Okay, welcome back to BME 2315. Today we're going to be continuing our work on looking at how to do calculus on data using, in this case, integration, while last time's lecture was on differentiation. So as we discussed, the robotic arms in surgeries are equipped with lots of different sensors to look at, measure exactly where they are and control where they go inside the body to do very precise surgical manipulations. And these types of accelerometers are used all over the place for robotic arms and surgical tools, and also other types of biomedical instrumentation. And last time we talked about how to do numerical differentiation, and so this time we're going to be looking at how to do numerical integration, which is an important operation on these robotic devices. So overall, the learning goals for this section are to be able to explain how numerical integration algorithms work, to look at the advantages and disadvantages of different methods that we'll be able to use, and to understand how changing the order of our function or step size affects the error. And finally, you're going to be applying these algorithms that we'll talk about to both idealized functions and real biomedical data on your problem set. So most of the integration formulas that we think about are in a class called Newton-Cotes integration methods. And the basic idea is if you have a function such as this of f of x, and it may be going from a to b, and what we're doing in integration is try to calculate the error or the area inside or under this curve. And in calculus, we say that the integral is the integral from a to b of f of x dx. And in the Newton-Cotes integration methods, what we're going to do is we're going to replace this f of x with a simpler f of n function where f of n is a polynomial like this. And we're going to use this to our advantage because taking a integral of these polynomials is often much easier to do than for more complex functions. And so we're going to be, the general form of the answer will be as the width of the interval from b minus a times the average height. And so this right here is the width. And so we're going to be talking about three different types of approximations where we use different approximating polynomials as different ways of calculating the average height of a function over some interval. So the simplest approach that you might imagine would be a linear approximation. So if your function looks something like this, and it's going from f of a to f of b, and we're going to just assume that our line f of 1, in this case, we'll call it f of 1, is our first order approximating function, is linear. And so then what we're going to be doing is calculating the area inside this. And so if you look back to how we described this before, we said that our approximating function is this f1 and a0 plus a1x, and it equals the width the integral is the width times the average height, where the average height is given by f of a plus f of b. Okay, so this is the height right here. right here. And so that's like a very simple integration formula right here. And we say that that the error, this is an equation, a more precise definition for the amount of error, but it's on the order of 1, okay? Meaning that that is a constant based on the distance over which we're integrating. Okay, so let's now apply that in an example. Let's say we're looking to integrate 8 plus 4 cosine x from x0 to x pi over 2. And so we just have 2 locations. So I'm going to make a little number line here. 0 to pi over 2. So it's a very simple little new number line. And we say that we want the pi over 2 fx dx. Okay, and then we're going to apply our little formula for calculating the numerical integral right here. And so that's going to give us the b minus the a, and then we're going to multiply by f0 plus f of pi over 2 right here. And that gives us pi over 2 times, and you look at what is this function at x equals 0, it's 12. And what is this equation at pi over 2 is 8, like this. And if you calculate that through, you should get 15.708. Okay, and it turns out that the actual true value of this, if we weren't approximating it, is 16.566, which gives us a true percent relative error of 5.2%, which is really not that bad considering that we're taking a very curvy sort of function and approximating it as a line, and we still got a relatively accurate result. Okay, so how can we do better than just approximating our function as a single trapezoid? Well, we can break it up into multiple trapezoids. So for example, if we have a function that looks like this, we could break it up into one trapezoid right here, and another trapezoid over here. Okay, where this might be the area under this one, this would be the area under this one. And so we can actually just apply what we learned in the previous one to apply it to each of these individual trapezoids. So we'd say that I equals b minus a over 2, because it's like half the interval, times f of x0 plus f of x1. I'm going to divide by 2. So that's for the first trapezoid. And then for the second trapezoid, it's going to look the same initially, f of x1 plus f of x2. Okay, and if we add these two together, what you're left with is a b minus a, which is the overall width, equals 1/4 f of x0 plus 1/2 of f of x1 plus 1/4 f of x2. Okay, so this is a formula for if you're going to use just two trapezoids. Okay, so that looked like a better estimation than just one trapezoid. So now let's look at how it expands to even more segments. So for n segments, that means the little intervals. It's given by this equation right here. where we still have the width, but we've got a more complicated equation for the average height of our function. And so for n segments, then that we're going to require n plus 1 points, because, and you can see that from the equation, because it's going from x is 0 to f of xn. Okay, so you need a total of n plus 1. And what that is doing then is it's breaking up, if you have a complicated equation like this, it's breaking it up into lots of little trapezoids. And so you can see that going from A to B in lots of little trapezoids. And so you can see as you break it up into smaller little bits, it should more closely follow the curves of the function. And so because of this property, the error on the multiple application trapezoidal rule, like here, is 1 over n squared. So basically, if as n goes higher and higher, you get much lower overall error in the system. Okay, so now let's do an example using this multiple application trapezoidal rule. So, so what we're going to do is we're going to be doing our same function as we did before, but let me show just a little number line in this case. So we start off at 0, and we're going to pi over 2. And then in the middle we have pi over 4. Which means we've got pi over 8 right here, and 3 pi over 8 right here. So there's a little number line to keep track of what points we're talking about. And if we use this little equation here, we get that, let me just specify here, is that x0 is where it's at 0, and f of xn is going to be at pi over 2. Okay, and so if we use this equation, we'll see that b minus a is pi over 2 over 2, pi over 2 minus 0. Okay, and then the 2n right here is n equals 4. Right here. And then we have to look for the first term is f of 0 plus, and then the coefficients are 2, so 2 times f of pi over 8 plus 2 times f of pi over 4 plus 2 times f of 3 pi over 8 plus f of pi over 2. Okay? And so if we put in, throw in your calculator and compute what each of those function values are, you should get 16.515, which you can see is much closer to the true integral of this equation. And all we're doing is really breaking down this cosine function and approximating it as a series of trapezoids. So the error on this, if you compute the true relative error, is 0.31%. And so that's actually like a very good approximation. And remember that the ET, percent ET, is defined as the true minus approx divided by true times 100%. Okay, so to summarize so far, we said that in the trapezoidal rule, we could approximate f as a linear function and numerically estimate its integral in that way. But if we increase the number of segments using the multiple application rule, we can improve the accuracy of our estimates. So what's coming next is that we're going to be looking at how we can use a little bit more complex approximating functions, either as a quadratic or a cubic, to better and better estimate the integral of our functions. So see you in that video. Bye.